Okay, well, welcome back to our discussion on neural networks and how that can be used for machine learning. We have had a couple different types of models seen in this lecture, looking at how we construct a neural network. So let me go ahead and I'm just going to review a couple of those slides and point out a little bit more than what I've done so far with some of these points here. So we have these three functions. You evaluate the inputs. So we can see that each one of them has a weight. You calculate the total. So here that would be the second thing that we do. And then the third thing that we, well, let's take it one step at a time. Here we have, there's some type of a gain factor here that's listed. So maybe this is 2A, and then we have, say, 2B, and then we have 2C, where we do this thresholding, and we spent some more time talking about that. And then as a result of this thresholding, we're able to come up with an estimate of what the output should be. And so that would be item number 3. So that was one of the ways that we looked at for that. We then, one part at a time, looked at things in more detail. And so we have these thresholding functions. And so say like you come up with a summation of values that were seen from this kind of a model. And we want to have that decision to be either one or the other. Well, when you do that summation and the fact that we're dealing with inaccuracies, what if that value ends up being such that it's not just a 0 or a 1? So we want to have this thresholding factor, so it's going to be very easy. So once it's above a certain threshold, you're going to call this a 1, even if it's maybe as low as 0.6, 0.7 or something like that. So that would be one type of a thresholding that we could be using. And then we showed another example, say if we're going from -1 to 1. So we have an example going from 0 to 1. We have another example going from -1 to 1. Then we talked about, well, what if we start to aggregate this together into a neural network? And so this is a feed forward network. So we're taking information that we get from one step and then we feed it into the next step. Here we have inputs coming together. And so we're evaluating each one of those one at a time. So this is a 2-layer network. So we can see that, and then we coming up with the outputs that we're showing there. We then started to have a discussion that got pretty technical in terms of how to be doing error corrections. And so there's a couple different ways that we can be doing that, and then putting in a couple of values to help us to work out how and what it means to be tracking those errors. So you can look over the charts to get a better sense of that. With that, I think one thing I'll be pointing out here is the fact that we have these partial differentials that we're using. And so we have a differential function, so we can find the relationships for one particular value. And so say for, well, what is the sensitivity for this? So you look at the error function with respect to a single type of W value. And so that's where we have this partial differential type of equation set up. All of this is captured when you're doing things in, say, MATLAB, Python, or whatever, when you have it codified. But we're trying to give a little bit of a perspective of the algorithms by what we're doing with this type of course. And so this is where it's a nice summary set of charts that are also in the textbook. And so you can read more of the network. So first we have the forward propagation. So we had the one diagram that looked a lot like this. And so that would be this one. But this is now just focusing on one outcome that we're trying to identify. And so with the result of all of these different inputs. The error signal back propagation. And so we can be remembering the error for each time we do this. And so then we can feed that back as we continue to be doing processes. And so that's an example of that. We talked about more elaborate type of these type of nonlinear functions of, and so that was another thing that is captured. So various types of nuances and interesting details that we're capturing with our discussion as we went through that. So I want to just spend a little bit more time going through some of those charts, trying to just give an intuitive sense without getting too much into the mathematics. Finally, there's just one more concept that we'll talk about, and that's the multi-classification discrimination with MLP networks. So for multi-layer perceptrons, MLP networks can be used to realize nonlinear classifiers. And so most real world problems require nonlinear classifications. And so it can't be done with just simply saying it's above or below a line, if you will. So a realistic approach is a 1 of m encoding. A separate node is used to represent each possible class, and the target vector consists of zeros everywhere except for the element that corresponds to the correct class. So for a 4-class example, so m equals 4, the discrimination problem, that the target vector would be as we're showing there. To encode 4 possible classes, here we have this, and so we have this. These are vectors putting together, it's a matrix, and so this is how we encode for class 1, 2, 3, and 4. 4 log sigmoid nodes are used in the input layer of the MLP network. The binary output value are used. So, and then just to finish up, once the network has been trained, performing the classification is easy. Simply choose the element y hat k of the output vector that is the largest element of y, for i.e. for y hat k, for which it's greater than everyone else. And this generates an unambiguous decision, since it is very likely that the 2 output neurons will have identical output values. So with that, that's an overview of neural networks, and we'll continue on and with the next lecture. Thank you very much.